Good afternoon, everyone. Folks, this is just to give you a recording notice being recorded. If you have any concern, you need to contact me. Now, what we are going to continue today, last week, we started joint probability distribution. That's what we started in our last lecture, distribution. Now, we will continue this joint probability distribution today. There are some properties that we need to discuss first, and then I will go into some more details. The first property is the independence. Independence. Now, if x and y are mutually independent, the joint probability distribution, as we were denoting it as a P of x of y at x is equals to x, and for y is equals to y, that is equals to the product of these two probabilities. The first one is P of x, and then we multiply it by the probability of your second variable, which is P. This is your y. So if x and y are mutually independent, the joint probability distribution P of x of y becomes the product of two probabilities. Now this is for your discrete random variable. In case of continuous random variable, we will have f of x of y. The rule remain the same. It will be the product of these two probabilities, f of x times your f of y. Now this approach of taking the products of two probabilities when they are mutually independent is the same as you might have been doing this in your statistics classes, that the probability of A intersection of B will be equals to the probability of A times probability of B. Now the same concept apply here. If they are mutually independent, we just take the product of their probabilities. Now this second equation is for continuous random variable. Folks, I need to go to the next slide, please. Now the second property is the expected value, or we also called it as a mean. Expected value and the variance. Now if joint distribution joint distribution for two random variable or two random variables. Now in our case we are saying them as x and y, is known then the expected value and variance of x and y can be found as below. Now the first I'm going to write down the relationship for discrete random variable. Discrete random variable. The expected value of x is, we also denote it as mu of x, equals to, we take our x values and we multiply it with the joint probability of x and y, and then we summation of both of them. So it will be all x values and the second one is for all y values. In case of value for our random variable y, we have mu of y. So that is equals to, we take our y values, we multiply them with our probability values, p of x of y, and then we sum up both of them. This is my all x and this is my all y. So just to repeat it, we have the joint probability distribution and we multiply it with x if we are interested to find the expected value of x. In case of the y, we take the joint probability of p of x of y and then multiply it with the y variable, and then we take the sum from all x and all y. Folks, I need to go on the next slide, please. Now this for the discrete random variable. In the next slide, I'm going to write down for continuous random variable. So the only difference will come out, we will take the integral values and our joint probability will change. Now for continuous random variable, we have the expected value of x, or we also call it as mu of x, that is equals to, we take our x values and we multiply it with the joint probability of continuous random variable, which is denoted as f of x of y into x of y, x and y. Now here we need to be careful. We will have the integral values, and The first integral goes from minus infinity to infinity. The second integral goes again from minus infinity to infinity. Now this inner integral is for d of x and the outer one is for d of y. Now in case of e values, expected values of y variable, we have mu of y. Now in the same scenario, we will have the y value needs to be multiplied by the joint probability distribution of x of y. And again we have the two integral. It is going from minus infinity to plus infinity. This is also going from minus infinity to plus. And the internal integral is for d of x and d of y. Now we will look for the variance. Now for discrete random variable, we have the variance of x. This is also represented as sigma of x square is equals to. Now we take our x square. Because we are talking about the discrete random variable, I need to have the joint probability in terms of discrete random variable, which is noted as x of y. And then we sum up here. This is for all x and this is for all y values. Now the only difference comes here is the x square. Once you solve all this, then you subtract the mu of x square value from this. Just keep in mind, when you are solving it, we will do some numericals, of course. This is the first term, and then you subtract it from your square of your mu value. Now in the same scenario, we will write down the variance formula for y variable. The same logic here. I start with the y square values. Because I'm talking about discrete random variable, joint probability distribution is denoted as, in terms of a discrete random variable, as p of x of y. And then we sum up these values. This will be for all x, this will be for all y. And once you have solved this, this should be subtracted from your mu of y square. Now these formulas of the variance, now these formula of the variance, they are on the same formulas as we were discussing before. If you recall from our previous lectures, let me do it here. That was the x square times your probability values minus the mu square. This is what we were doing previously. It's the same formula, but for the two variable x and y. Now this variance, these variance formulas, these were for your discrete random variable. In the next slide, I'm going to write down for the continuous random variable. Now for continuous random variable, our sigma of x square is equals to, now the logic remains the same. I have my x square values that should be multiplied by the joint probability distribution in terms of continuous random variable, which is denoted f of x of y. And now I take the integral here because I'm talking about the continuous random variable. Integral from minus infinity plus infinity, minus infinity to plus infinity. And the first inside integral will be for x, and the outer integral is integrated for y. Now, similar to the previous, uh, we subtract the square of our mu value. And because we are talking about the x variable, it will be for x. Now, similarly, I can write it down mu of square. This will be, I have y square values. Those should be multiplied by the joint probability f of x of y in terms of continuous random variable. And I take the intervals. This will be from minus infinity to plus infinity into d of x times d of y, which is for the integral, and we subtract our square value because we are talking about the y variable. It should be for y. Folks, I need to go to the next slide, please. Now, another property of joint probability distribution is the covariance. Covariance. Now, this word comes from combining the variance of more than one, of course. It is covariance. What is the definition of this? It is the measure of linear relationship between the random variables So it is the measure of the linear relationship between the random variables. Now besides, okay, let's write it down. Besides the mean and variance for joint distribution, covariance is also used. It is used to describe the degree of association between x and how do we denote the covariance? It is written as C, this is C, COV of x, random variable x, and y. And its formula is expectations of x minus mu of x multiplied by y minus mu of y. Now this is also represented as sigma of x of y, because you know this denoted for the variance. Now these terms are also solved as expectations of x and y minus expected value of x times the expected value of y. Now if you recall from your previous lectures, these terms, this one we can denote it as mu of x, and this term we can also denote as the mu of y. Now this term, the first term here, expectations of x and y, it has two different formulas in discrete random variable and continuous random variable. And in the next slide, I'm going to show you that. Folks, I need to go to the next slide, please. Now, in discrete random variable, expectations of x and y is, now because we are talking two x and y here, our x and y, we multiply it with the joint probability distribution. Because we are talking about the discrete random variable, the joint probability distribution is represented as P of x of y into x of y. And because it's a discrete random variable, we sum up all the values. And there are two variables, so summation should be for 2. This is all x, this is all y. Now in case of continuous random variable, this expectation of x and y is equals to, again the same logic, we have x and y, two variables, we multiplied with the joint probability distribution, and in terms of continuous random variable, it is noted as f of x of y into d of x, and then we take their integrals from minus infinity to plus infinity, minus infinity to plus infinity, in case of continuous random variable. The covariance, that's showing the relationship between two variables. Now if x and y are independent, then your covariance of x of y will be equals to 0 because there is no relationship between them. They are independent of each other. Folks, I need to go to the next slide, please. Now, there is another measure of the linear relationship we use, which is easier to interpret. It is called as the coefficient of correlation. So let's write it down, and there is another measure of the linear relationship. This is T between two random variables that is easier to interpret than the covariance. This is called coefficient of correlation. Correlation. This point easier to interpret. I will come back to this and explain you what does it mean. Just bear with me. Now we have two terms here. One is called covariance, other is called as the coefficient of correlation or correlation sometimes. What is the difference between them? The covariance it is used to determine how much two random variables vary together. Okay, covariance it is used to determine. I think I write down the wrong spelling here. Let me correct. It is used to determine how much two random variables vary together. Now, in case of correlation or the coefficient of correlation, it is used to determine this time these are okay, I guess, right? Okay. It is used to determine when a change in one variable, a change in one variable can result a change in another variable. So covariance is used to determine how much two random variables vary together, whereas the correlation, it is used to determine when a change in one variable can result a change in another variable. And both of them are used for the linear relationships. Folks, I need to go on the next slide, please. Now, I'm going to draw a graph here, two graphs here, and will explain you these points. So for example, this is my variable x, this is my variable y. The second graph is, let's say this is my variable x and this is my variable y. And the covariance formula that we just studied is covariance of x to y is equal to expectations of x minus mu of x times the y minus mu of y. That's the formula we just studied before. Now, in this graph, I'm going to develop a positive relationship. By that, I mean to say this will be a straight here. It has a positive slope and it is giving me a positive relationship between x and y. So this one is for the positive relationship. By that I mean to say if x is increasing, as you can see here, the y will be increasing correspondingly. That gives you a positive slope here. Now in this graph I'm going to take the negative relationship. By that I mean to say if x is increasing, the y is going to decrease. And this is the negative relationship here. So this is my positive relationship between x and y. And this is my negative relationship. Now I'm going to develop some scenarios here. For example, if x value is greater than your mu of x. Now what will happen in this here? You have x value is greater than mu of x, you will get something positive number. And because x is changed, y is changing with respect to x due to the relationship, this y will be higher than mu of y as well. So I will get a positive number here again. This is going to give me a positive number again. So when I multiply positive number by the positive number, my outcome is going to be a positive. This is my outcome here. Now in case x is less than your mu of x, so what will happen here? Because x is less than mu of x, I will get a negative number, of course. And because y tends to go in the same direction according to this relationship, your y will be negative number as well. So if I multiply negative number, multiplication is happening here. If I multiply negative number with the negative number, I will get the positive number again. So I can say that in the positive relation, in the positive relationship between x and y, my covariance will be positive. Now let's come back to the second scenario where we have the negative relationships. I'm going to take the same here. I will say that x is greater than mu of x, just like we were doing here. Now, this is my x is greater than mu of x. Again, I will get a positive number. However, over this case, the y is not increasing with x, it is decreasing. So because with the increase of x, the y is decreasing, this will be a lower value than mu of x. So that's where I get a negative number in this second. And when I multiply positive with a negative, the outcome will be a negative number. Now let's take this scenario here. When x is less than mu of x. Now in that case, this term will be negative. However, because here again the same relationship, like the y will be increasing because x is decreasing. So I get a positive of the second term. And when I multiply negative by the positive, I get a negative number again. So I can say that in the negative relationship, of x and y, your covariance will be negative. Folks, I need to go on the next slide, please. Now, this is the whole story of your covariance. Now, where does the coefficient of correlation comes in? I'm going on the next slide, please. Now, the same formula for covariance of x of y. So this would be x of y. That is equals to your expected values of x minus mu of x times y minus mu of y. Now these are two different variables in the covariance. So for example, this can be, let's say, the height of the person in terms of centimeter and the weight of the person. This is another variable, kg. Now if you look on the units here, the final units turns out to be centimeter times kg. Now the units does not make sense because they are totally different units. We cannot compare two different units. It is just like you are comparing the apple with the oranges. Now, in order for us to compare the variables, the units should be the same. So, if we want to compare variables, we cannot compare them as units are different. As I said, it is just like comparing apple and the oranges. So I cannot say like if 10 kg of the weight is comparable with how many centimeters? We can't answer this question. So what we do, so we normalize. This is W here. So we normalize this and make it unitless or dimensionless by using correlation. Now the correlation is denoted as rho of x of y, and its formula is sigma of x of y over sigma of x and times sigma of y. Now if you see here in the correlation, we have the same quantities on the numerator and denominators which cancel out their units. So I'm getting a dimensionless number which can help me to compare the two different random variables. This is why on my previous slides I write that this is easier to interpret. Now with this correlationship, I can easily compare two variables. Now if you recall the definitions of sigma of x, that was sigma x square, and the other definition of y is the same. So this equation I can also write it down as rho of x of y is equals to, this is my covariance here on the top, so this is my covariance of x and y, and here I have the square root of variance of x times the variance of y. Folks, I need to go on the next slide, please. Now, as I said, we are making it a unitless by normalization. Your correlation value will be greater to -1 and will be less than equals to 1 always. Now, if I have rho x value equals to 1, 1.0, I would say that x and y have high positive linear relation. Now here you can see we don't need the units of x and y. If your correlation is the negative, let's say -1.0, then your x and y have a high negative linear relationship. Folks, I need to go to the next slide, please. Now I'm going to draw some graphs to explain these points here. So this is the graph I just draw earlier. So if you have x and y, and for example, these are the points that you are getting. So we connect them and we find out that this was a linear line. And if you remember this equation for the linear relationship, y is equal to ax plus b, this is the slope of the line. So in this case, your rho of x of y is the 1. Now, second possibility could be, if this is my x and y graph, so you can have some dots which are approximating your linear relationship. In this case, example, your rho value can be, let's say, 0.8. Or I can say that your rho of x is greater than 0 in this case and less than 1. For the negative slope, which I also draw in the previous, if you have this x and you have the y, and again you have a straight line, but this slope is the negative slope. So in that case, you will have rho of x of y as a negative, -1. Folks, I need to go on the next slide, please. Now, other than straight lines, you might have a graph which is something like these points. So when you connect them, you find a shape which is similar to your parabola. And if you remember the general standard form of the parabola, your I will be is equals to a of x square plus b of x plus c. And again, the graph is between and your y. Now, as you can see here, the x and y, they are highly correlated. But because these are not linear, in this case, your rho of x of y will be equals to 0. Because this is not the linear relationship. Is not linear. So then your rho value will be 0. Now when your correlation is 0, a correlation of 0 means there is no linear relationship. It does not mean there is no relationship, it only means there is no linear relationship. Between x and y. Between x and y. And as we said in the previous slides, if two variables are independent, your covariance will be 0. So your covariance of x and y will be equals to 0. Now, similar to the previous graph, there could be a situation where we have the graphs with some random points here. Let's say some random points you can draw. Now, in this case, again, our coefficient should be equals to 0. That's because there is no linear relationship. Now, the general formula for variance of a of x, a is the constant, plus minus b is the constant of y, is equals to a square variance of x plus b square into variance of y plus minus 2ab covariance of x and y. Now, if your x and y are independent, we just learned that this covariance terms, covariance of x of y should be equals to 0. So if I put this value of 0 in this equation, what I will get, my variance of a of x plus minus b of y, those will be a square variance of x plus b square of variance of y. Now, in general, we don't subtract the variables, so I can eliminate or delete this negative from this equation, because this negative, positive negative, only makes sense if I'm using the third parameter here, but because they are independent, it has been deleted, and generally we don't use it for the negative, so in this equation, just delete my negative. So what I'm going to erase, I will erase my negative here. So that's my equation I use when the x and y are independent. In this equation, a and b are constant. A and b are the constant. Oops, I need to go to the next slide, please. Now, there is one thing that we use it as the marginal probability distribution. Or we also called it as marginal distribution. If the joint probability distribution for two random variable x and y exists, then the individual probability distribution of a random variable x and y is called marginal distribution. So basically, the marginal probability distribution is the individual probabilities of your x and y. Now, if I have this joint distribution of x and y, if x is equals to x and y is equals to y, then folks, I need to go to the next slide, please. Now, P of, how do we find the marginal probability? P of x is equals to P of x we take the summation here and P of x of y of x of y. Now there is one important thing to do once I write down the equation for y as well. So the probability, marginal probability for y is equals to, this is also the marginal probability, another notation for this is equals to the summation of P of x of y into x of y. Now I'm going to do very important thing which you need to pay attention, and I'm going to use a different color just to highlight what I want to say here. When you are using the x marginal probability, the summation should be y, not x. So it should be all your y values. If you are using marginal probability of y, if you want to find out the marginal probability of the y, the summation is all x. This is the very important point in the joint probability distributions. That's why I wanted to write it in a different color. Now these are called marginal distribution. Marginal distribution. These are the same probabilities as you used to find for if you have two events A and B and you want to find out the individual probability. We did a numerical about this as well. That's what in terms of joint it is called as the marginal distribution or marginal probability distribution. It could be any other variable, probability of B, let's say. Now the same rules apply for the marginal probability distribution, that your probability values of x will always be greater than equals to 0, and sum of all the probabilities of x will be equals to 1, and similarly the probabilities of y will always be greater than equals to 0 and equal to 1 even, and the sum of all your probabilities of y, these should be equals to 1. Folks, I need to go to the next slide, please. Now in next slide I'm going to show you how we find them. This approach, all y, how we use it. Now if you recall, in our previous lecture we had a table like this, that we had y here, and we had the x, we had the 0 value, 1 and 2 for x, and the y values were 0, 1, 2 and 3. This value was 0 0.39, 0 0.06. I'm just going to write down some values, not all. At 1 it was 0 0.48, at 2 it was 0 0.02, at 3 it was 0 0.01. Now just for your recall, if I take any of this value, let's say this value was, let's say I take this value was the joint probability of p of x of y, and we write it down at x is equal to 1 and y will be 0. This was 0 0.06. This is how we used to write it. Now I'm going to delete it because I need to use this space here. And then you have other values as well, which I'm not writing here. Now, if you want to find out the marginal probability of y, let's say at is equal to 0, what you need to do, we will take the marginal probability values at all values of y at 0, and we will take the x values, all values of x. That's what I mentioned the last time. So it should be probability of x equals to 0, y at is equal to 0, plus the probability of x is equals to 1 and y is equals to 0, plus the probability of x is equal to 2 and y at 0. Now as you can see, I'm interested for the marginal probability distribution of y at 0. The y at 0 remain the same, but I'm changing my x values. So let's come to this table. Now this value means x and y at 0. X at 0 and y at 0 is the 0.39. So it will be 0.39 plus, at x is equal to 1, my y is equal to 0, which is 0.06, plus this value at x is equal to 2 and y is equal to 0 is 0.01. So that's what your answer is, 0.46. Now this values, marginal probabilities values, if I sum up all of this, I get the value of 0.46. So here I can say that probability of y. Similarly, if you add up these values, you will get a number. If you add up these values, you will get a number. When you add up these values, you get a number. Now, if you want to find out the marginal probability when x is equal to 0, in this case, the x remain the same, whereas we change the y values. So what that will be formula when we expect? So it will be x is equal to 0 and it will be y is equal to 1 plus marginal joint probability at x is equal to 0 and y is equal plus the joint probability of x is equal to 0 and y equals to 3. Sorry, I missed a 0 here, so it should be it should be 0. So this will be at y is equal to 0. This is y is equal to 0. This is, sorry, 0, and this should be 1, and this should be 2. And because for the y we have the up to 3 point we have, so it is the p of x is equal to 0 and at y is equals to 3. Now at x is equal to 0, y is equal to 0, my value is 0.39. So this will be 39 plus at x is equal to 0 and y is equal to 1, I have 0.48 plus at x is equal to 0 and y is equal to 2, I have 0.02 plus at x is equal to 0 and y is equal to 3, I have 0.01. So that's what gives you a 0.9. So on the right hand side of this one, I can say that I have the marginal probabilities values. This particular value is at x is equal to 0. Marginal probability distribution of x is equals to 0. With the similar procedure, you will have one value here, one value here. Once you add up these values and these values, they should come up equals to 1. So sum of all these probabilities values will be equal to 1 and sum of all these probabilities value will be equal to 1. This thing will verify that your calculations are correct. Now once you have completed this table and let's say I eliminate this value, you can easily find out what was the missing value here, because you know the sum of all this should be equal to 0.9 and sum of all these should be equal to this value. So you can easily find out your missing value. Okay, folks, I will stop it here. Numerical, but we can do it next time. If you have any question, please ask me. Folks, is there any question for me? It seems like you don't have any question. I just need to make an announcement before you leave. Folks, on Monday, October 26 at 2 p.m. we'll be arranging an informal meeting. The purpose of this meeting is to take the feedback on the course. I also want to hear if you have any challenges in your course and how can I help you to deal with those challenges. This meeting of Monday will not be recorded. Will not be. So I wish to have your video turn on so that we can see each other and have some conversation about the course. I will send you an invite of this maybe today or tomorrow. It will be very informal meeting. I just need a feedback from you and what kind of the challenges you are facing in the course and how can I help you. Folks, is there any question for me? This meeting will also help you to learn more about your classmates. I decided this time because this is the best time. Can we discuss project related matter on Monday's meeting? I need the course feedback actually. If this is related to your course feedback, then you can discuss it, Sabiuddin. If it is a very particular question, then you can email me and we can set up a separate meeting for this. Okay, Sabiuddin? Folks, is there any question for today? Now, one thing you have is I have not given you anything from the textbook so far for the joint probability distribution. That's because there are 3D graphs which you need to learn. Only then you can work on the numericals. So hopefully in the next lecture, we will have some numericals and I will explain you those graphs and then I will provide you some examples and numericals for your practice. Folks, are there any more questions for me for today? Thank you very much. If you don't have any question, I will just let you and I will see you on Thursday. Thank you, everyone.